In your previous classes and papers, you have already discussed about vector spaces, inner product spaces, metric spaces, and so on. So likewise, we have the topological space. And before starting with the topological space, you need to learn the definition of topology. So let X be a non-empty set and T be a collection of subset of X that satisfies the following three conditions. That is, the null set belongs to T and the whole set X should also belongs to T. And if you take any two subcollection G1 and G2 from T, then the intersection of those two subcollection should belongs to T. And the third condition is that the union of all those elements of any subcollection of T should be in T. Then T is a topology on X. T is said to be a topology on X. So let me give you an example. Let's X is equal to A comma B comma C, and T is a collection of subset of X such that T is equal to the null set, the whole set A comma B comma A comma B. Then we can say that T is a topology in X because the first condition is that the empty set phi is belonging to T and the whole set X is belonging to T. You can see that. And then the second condition is that the intersection of any two subcollection of T should be in T, right? So we can say that if you intersect A and B, then it will give you 0. Let me show you over here. So let's take A intersection B. It will give you the null set, and the null set belongs to T. So likewise, if you take any two subcollection, if you take the intersection of any two subcollection, it will always belongs to T. And likewise, we have the third condition, the union of all these elements of subcollection of T is in T. So let's say, let's take again A union B. It will give you A comma B, right? And it belongs to T. It belongs to A comma B belongs to T. And if you take let's say X union A, it will give you X, which also belongs to T. So from this we can say that T is a topology on X. All the three conditions are satisfied. So it means that T is a topology on X. So let's give you another example. Let X is equal to A comma B comma C and T is equal to phi comma X comma A comma B. Then T is not a topology in X because let's say the first condition is that the null set and the whole set belongs to T. Yes, but what happens is if you take A and B, if you take the union of A and B, then it will give you let's say A union B, then it will give you A comma B. But A comma B does not belongs to T. There is no A comma B in T. So it means that T is not a topology on X that satisfies the following. The second condition is not satisfying and the third condition is not satisfying. So it only has the phi, the null set and the whole set, but the other two condition it fails to satisfy. So it is not a topology. So likewise, talking about the topological space, if T is a topology for a non-empty set X, then X comma T is said to be a topological space. Understood? So the next we have the types of topology, and the first one is the indescript topology. Let there be a non-empty set X, then the collection I consisting of the empty set and the whole set is always a topology for X, and it is called the indescript topology. And this space Xi is called the indescript topological space. We know that we have this null set and the whole set. If you take the union or the intersection, then it's always belong to I. So this kind of topology is called the indescript topology, and this space is called the indescript topological space. The next one we have the descript topological space. Let D be a collection of all the subset of X. Then D is a topology for X called a descript topology. What we are trying to say is that if you have a set X consisting of these elements A and B, and you take the whole if you take all of the subsets, that is what are the possible subsets of X, that is first one is the null set, the whole set, that is X itself, then we have A, then we have B. Then it is a descript topology because if you take any two subcollection and take intersection or union of those two subcollection, then it always belongs to T. So such type of topology is called the discrete topology. And the next we have the cofinite topology. Let X be any non-empty set and T be a collection of those subset of X whose complement is either finite or is all of X. Then T is the topology for X called the cofinite topology. So it is simple that if X is any non-empty set and T is a subcollection of those subset of X whose complement is either finite or all of X, then T is a topology for X called the cofinite topology. And we have the next one is not that important, but like you can say co-commutable topology. Let T1 and T2 be two non-empty set and let T consist of all the subset of X whose complements are either countable or is all of X, then T is called co-countable topology. So that's it for today. So you can follow me on my Instagram and you can subscribe to my channel for more videos.